Okay, so now let's move on to natural language processing. So this is going to be an introduction to NLP. So let's firstly start with what is NLP? So NLP is a subfield of artificial intelligence that deals with the processing and understanding of human languages. It is the foundation of language translation, topic modeling, document indexing, information retrieval and extraction, and lots of other applications in the language domain. So some current hot topics in NLP involve search engines, chatbots, sentiment analysis, summarization of documents, marking essays, and grammatical checking and improving writing, as you can see with stuff like Grammarly as well. So NLP's role in business, one of the core examples of this is in translation. It helps so much when you have to communicate with people from different countries who speak different languages. It has basically made our world a lot smaller and a lot easier to communicate in. What about summarizing information? I find this quite useful. This is TripAdvisor here, where basically they can actually pull out clusters or keywords that have been mentioned many times in reviews. Amazon does the same as well. And what about sentiment analysis? Suppose you run a big company and you want to see what people are tweeting about you. You can actually train a model to basically pick up the emotions in tweets, and you can actually plot this like daily and over time, so you can see how your customers or how people or the public are responding to certain topics. And what about chatbots? Because right now call centers basically have to be staffed by so many people, and customers hate waiting to get their issues addressed. So if you can have a chatbot that can emulate a human quite well, you can actually solve a lot of customer issues by just employing some chatbots. And what about information retrieval and extraction and search? Lawyers basically find something like this quite useful. You could look at other things like investigators or journalists who would want to actually pull up research fast or even get summaries of different stuff. So you can see there's a lot of different applications for NLP in business. Even things like autoresponders in emails, like Google and Gmail has this quite nifty autocomplete feature. So I've used this many times before, and it's actually quite good. I'm impressed with how good it is sometimes. So basically, this is what our chapter on NLP is going to deal with. We're going to talk about the bag of words model, tokenization, predictions. Then we're going to go into our case studies, sentiment analysis, which we look at airline tweets. Then we're going to look at some review summarization based on some Amazon reviews, and how we classify text. So we can do a case study on basically building a spam filter. So that's it for the introduction to NLP. Now let's move on to bag of words. So how exactly do we model language? And that brings us to the bag of words model. So let's take a look at it. So when training NLP models, we need to understand how we create or format our data. So normally in English, we've got hundreds of thousands of words, which begs the question, how do we represent our words as data inputs to a machine learning model? So this is a question I asked myself initially when approaching NLP projects, and I was amazed to see there were such developed methods of doing this. So firstly, let's take a look at what typical machine learning inputs look like. So imagine we have our input features being height, weight, hair length, and our output, who could be 0 or 1 for male or female. So we can train a machine learning algorithm on this. Similarly, we can have something outputting, this is like a regression type, a diabetes risk percentage output based on these input variables. So those are basically the types of data sets we've seen so far. So how do we represent language or English text? We use something called tokenization. So let's take a look at what tokenization actually is. Now, this is the process where we take an input string of text and split it up, or parse is used a lot in the NLP realm, into individual string elements. It is a vectorization technique that allows us to represent words as real numbers. This is a key part of what tokenization does. And bag of words basically employs tokenization to do this. So let's look at example here. Okay, bag of words and tokenization example. We have two sentences here. One sentence says, we have landed on the moon. The other sentence says, the USA has landed on the moon. So firstly, what we do is we split this sentence up into individual string pieces. So we have landed on the moon, and the USA has landed on the moon. So what we do now, we basically create a row to represent each sentence. And for each unique word in these group of sentences here, we have have USA landed on the moon. And we put for sentence 1, which is 1 here, we have was in it, yes, so it's 1, the was a 1, have was in it, that's 1. Was USA in it? No, USA was not in it. There's no USA in this sentence, so there's a 0 here. Similarly for has, so there's a 0 here, but landed on the moon, there's a 1, 1, 1. And similarly for sentence 2, the USA has landed on the moon, there's no we, so there's a 0 for the word we, and no have, so there's 0 here, but 1s for everything else. So as you can see, if we have groups of, say, dozens of sentences, each feature will be a unique word in the sentence. So you can see us having maybe a few dozen columns if we were to do, like, say 20 sentences, and we'll represent the occurrence of a word with a 1 or 0 for each sentence. This is basically an example of how we can do it for a paragraph as well. You can actually do word counts too as well, although we're not doing that before. We're just doing whether it occurred or not counting how many times it occurred. And basically this is just a summary of what we did before. This is the same thing here, and this is how it basically goes. So we have original document, document vector, what we're calling this here, and the class label. So class label being like, if we wanted this to be, if this was a negative of something and this is positive, we can have class labels here. This will be how we train our machine learning algorithm now. So imagine we have this group of data here as our input X, and this is our Y labels, and we can now you can conceptualize how we can train a machine learning algorithm on text data. Okay, so now let's move on to normalization, stop word removal, lemmatizing, and stemming. So now let's talk about normalization, stop word removal, and lemmatizing and stemming. These are key or core NLP concepts. So firstly, you have to know words are messy. Look at these sentences here. We ain't gonna get it in time. This meal was pleasantly exquisite. Vote for PSG LGD at the International 2019. Oh my god, lol. Just text me, please. Talk to you later. Or you what, mate? So as you can see, this is how we talk in English. Some are proper sentences like this. Some are, a bit mostly proper, yeah. However, and this one is mostly proper, but there's a lot of like coded things here that you're not going to actually know about for context per se. And this one is just a bunch of text lingo, and so is this one. So words in any language, and we're just using English here, can be extremely messy, and having an NLP project understand these types of text is going to be quite tricky. So that's why you're going to have to do a lot of cleaning and pre-processing on this data. So how do we go about this? So here's normalization types. We have case normalization, which is quite standard. Removing stop words, which we'll come to shortly. Removing punctuation and special symbols, and lemmatizing and stemming. So let's take a look at what case normalization is, which is very self-explanatory. It's simply the standardizing of all case for words found in our document. So example, changing sentences like, hi John, today we'll go to the market. We just uncapitalize hi and John, so we get it like this. Typically case doesn't actually change any meaning though. However, they can in some cases, pun intended, where it can. Examples, alright, some examples of it. By the way, the pun was case and case normalization, in case you missed it. Reading is a city in the UK which is different to the act of reading, even though it's spelled the same. April and May are both common names and months, so you can see why capitalization, and actually they're both capitalizing when they're names and months, so it's even more confusing at that point. So you can see why case normalization isn't always the clear-cut answer to basically standardizing meaning of words. So also let's talk about removing stop words. Stop words are common words that do not add additional information. This should be add, not act, or predictive value due to how common they are in normal text. Examples of common stop words are things like I, is, and, a, are, the, or it, a bunch of other words like that. Basically stop words, and while they do convey meaning, from a machine learning perspective, they don't actually add much meaning to what a text is saying, usually. So what about removing punctuation and special symbols? That's a way to clean up data. Again, it's self-explanatory, but it's also a very important step in the cleaning process. However, there are instances where punctuation adds meaning, such as its, which is it is, versus its, which shows belonging. Example of punctuation and special symbols that are typically removed are all of these symbols here when we're doing an NLP project. So this brings us to the final one, lemmatizing and stemming. So both lemmatizing and stemming are techniques that seek to reduce inflection, the inflection forms, to normalize words with the same lemma. So what does that mean? Lemmatizing does this by considering the context of the word, while stemming does not. However, most current lemmatizers or stemmer libraries are not highly accurate though. But this is an example of it here. We have caresses being caress, ponies being pony, caress being caress again, cats being cat. So basically, as you can see, lemmatizing and stemming are just techniques to sort of like, inflection means like additions to the words, even verbs as well. So we sort of like take all the words like what it could be, variations of the word, and basically bring it back into one. So so you imagine if you had a bag of word models that had caresses and caress as separate words. They're technically not, they're the same word, just one is plural, one is single. Actually, one is like action, sorry, not the action and noun, I believe, not single and plural. Okay, now that leads us to the TF-IDF vectorizer, which stands for term frequency inverse document frequency. Okay, so this is going to be a fairly short section on the TF-IDF vectorizer, which stands for term frequency inverse document frequency. So let's take a look at it. So remember we talked about vectorizing text. So sometimes our good old bag of words model just isn't always good enough, and it's often a good way to explain how simple NLP classifiers are built, but in reality we need sometimes something more complex, okay? So methods that can account for the importance of each term in a document. That's what we need more of, okay? We need something that can account for this. So one of the simplest and most versatile vectorizers is called the TF-IDF, which is the term frequency inverse document frequency. So let's take a look at it. So the TF-IDF is the TF-IDF statistic for a term I in document J is calculated as follows. So you have TF, okay, minus IDF IJ is equal to TF times IDF here, okay, where, let's take a look at this. The TF IJ, remember I is basically a term in document J, is basically the number of times a term I is in document J over the total number of terms in the document. And the IDF I, which is used here, is the ln, basically, of the total number of documents over the number of documents containing the term I. That's essentially what the TF-IDF statistic is, okay? So now let's move on to word2vec, which is basically an efficient estimation of word representations in vector space. Okay, so let's talk about word2vec, which is the efficient estimation of word representations in vector space. Alright, which is a really cool system, you'll see it. So in previous slides, we explained why the bag of words modeling and the TDIF, basically how they work. And both are quite useful, but however, more advances in vectorizing documents have been developed since, and one such really good one is word2vec, which was developed by Google research team. So Word2Vec has been pre-trained over a large corpora, which is the plural of corpus, by the way. It uses an unsupervised learning method to determine semantic and syntactic meaning from word co-occurrence, which is then used to construct vector representations for every word in the vocabulary. Okay, so this is a bit confusing, so let's take a look at what it actually does. So you can read the paper here if you want to get a very good detailed understanding of this. Basically, we can summarize the paper, what it does, by this paragraph here, which is using a word offset technique where simple algebraic operations are performed on word vectors. It was shown, for example, that vector king and vector man plus vector woman results in a vector that is closest to the vector representation of the word queen. So basically, what Word2Vec kind of did was basically map out some very, very good clustering of words and their associations like this here. Okay, so we have male, female type words like this, verb tense, walked, walking, swim, swam, swimming, swam, I should say. And you can have country capital type mappings. So Word2Vec was trained over a large data set of data, the corpora we call it, and developed these types of representations. So training Word2Vec. So two model architectures were used to train Word2Vec, continuous bag of words and skipgram, and they both use a context window to determine the contextually similar words. Example, using a window of fixed size n means that all the words within n units from the target word belong to its context. Okay, and the context window here. So let's talk about what this actually is. So let's use a fixed window size of 2 on the following sentence. The quick brown fox jumped over the lazy dog. Let's look at fox as our target word, for example, fox in red. So the words in blue, quick, brown, jumped over, belong to the context of fox. Word2Vec, okay, by the way, just so you know, this is how we just do the pairings. Word2Vec has the ability Word2Vec has the ability that with enough examples of contextual similarity, the network learns the correct associations between words. That's what's so cool about the Word2Vec algorithm. So moving on from context window a bit, moving along with it, this assumption made by the design of the Word2Vec model is that words, this should be a model by the way, is that words which are used and occur in the same context tend to purport similar meaning. That's one of the assumptions they made. So the context window of Word2Vec is dynamic, which has a max size. The context is samples from the max window size with a probability of 1/d, where d is the distance between the word target. In our previous example, the target word fox using a dynamic context window with maximum window size of 2, brown jumped, okay, have 1/1 probability, 1/1 probability of being included in the context since they are one word away from fox, quick, over. Now these words have a half probability of being included in the context since they're 2 words away from fox. So I hope you understand now how we do the word associations basically here. So moving on now, so using this method, the continuous bag of words and the skipgram model separate the data into observations of target words and their context. So in a continuous bag of words case, in our fox example, the context is quick, brown, jumped over, and these form the features for the fox class. Now the skipgram, here we structure the data so that the target is used to predict the context. So we'll use fox to predict the context, quick, brown, jumped over. So hope this makes sense. So now we use Word2Vec to train a shallow neural network over data structured using either the continuous bag of words model or skipgram. So an example of this continuous bag of words model with a fixed context window of 1 on a simple corpus, right? So this is example here. So let's use our context window to include words that follows the target. In this example, we can assume that the words at the end of the sentence is the first word of the next sentence. I like math, I like programming, today is Friday, today is a good day. Like is the context of target I, math is the context of target like, programming is also in the context, also is the context of the target like, okay? Here we can see that the simple patterns emerge where math and programming are both contexts alike. So this is how we sort of build our neural network model for Word2Vec. Okay. So now we can move on to our case studies, our NLP case studies.
Subscribe now and press the bell icon. Never miss an update.